Okay, so another thing you might remember about conditional probability is that frequently information comes to us in the form of conditional probability, or we're theorizing in a way that sets up a conditional probability model. That's the way we kind of naturally think. If things are one way, the probability model is this. If things are another way, it's that. Um, that also works the same way with continuous random variables, but what we are writing to express the way it works looks different enough that we'll go through it in an example here. So let's start with kind of a basic example. So we're going to say the random variable is going to be how long do I have to wait for the bus? Okay, and we're going to talk about this in terms of the weather. Okay, so if the weather is good, the amount of time that I wait for the bus, it's my random variable x, that's going to be uniform on the interval 0 to 10. So I might have to wait 0 minutes, I might have to wait 10, and everything in between there is equally likely. If the weather is not good, then my waiting time is also uniform, but now it's on the interval 0 to 20. Okay, so just uh, longer likely, longer expected wait time, and higher variance when the weather's bad. That sounds like every bus system I've ever depended on. What we have here in words are two conditional PDFs. Okay, so the kind of the idea here, the new idea in this lesson is the idea of conditional PDF. Okay, so here. And what are they? Okay, well, we would just say the conditional PDF. The PDF of X conditional on G is 1/10 for X between 0 and 10 and 0 otherwise. And I'm going to erase what I wrote conditional PDFs. I'll just, because I want to use that space to write down the PDF of X conditional on not good weather, on bad weather here. Still function of X takes value 1/20 for X between 0 and 20 and 0 otherwise. And where did I get these numbers? In my mind, I kind of drew the picture and figured out what height these two conditional PDFs had to be in order for the area under the rectangle to be 1. And it was 1/10 in this case, 1/20 in that case. If you're not sure how I did that, go back to the first video in this lesson and kind of think about how to go from this words information to the PDF written in equations, or ask me about it. We can go through it. We can go through it later. Okay. The only thing that I say that's new here is this idea of a PDF being conditional. And of course, just like we said before, really all PDFs are conditional. We use this kind of notation when it's kind of important for the story that we're telling. But our probability models are always based on some things that we're accepting as true, some conditioning information. Okay. So this is just how we write a conditional PDF. And just as with any kind of probability function, any kind of conditional probability function has to obey all the rules of a regular probability function. So they have to, the probability of sample space has to be 1. They have to obey all the Kolmogorov axioms. All those things apply. And in a minute, maybe right now, we'll see that the law of total probability works as well. Okay, before we get to that though, just let me sort of make one observation. So if the question was something like, if the weather's good and if the weather's good, what's the expected amount of time I need to wait for the bus? That's a kind of question I would ask. Okay, and so we know that the formula for the expected value of a uniform random variable gives us the midpoint, or if we don't know that, we can look it up and remind ourselves of it. So the expected waiting time in good weather would be 5 minutes, in bad weather would be 10 minutes. The probability that I have to wait less than 3 minutes would be 30% in good weather and 15% in bad weather. So we could do all of these standard questions that we've been doing all along, and the fact that it's a conditional probability distribution doesn't affect the way we think about it at all. If we're in the world of good weather, this is our PDF and it works like any other PDF. The thing that we can do with the conditional PDFs is we can use the law of total probability to find the unconditional PDF if we know the probability of the conditioning event. Okay, so if we know, for example, that the probability of good weather is 75%, if it's 3/4, then here's how the law of total probability looks with PDFs. Okay, remember the law of total probability with discrete random variables, we took the weighted average of the two conditional probabilities, and those weights were the probabilities of the conditioning events. We're going to do the same thing with a PDF, so just check this out. The unconditional PDF for X is the PDF conditional on G times the probability of G plus the PDF conditional on G complement times probability of G complement. And if I was dividing things up into a finer partition, like if it was the probability of good weather, bad weather, and medium weather, I would have 3 terms here. The way I would know I was doing the law of total probability correctly would be if these probabilities of the conditioning events would have to sum to 1. I'd have to be covering the entire sample space here. So here we're just thinking about this simple partition of good weather versus bad weather here. And that is how we would find the overall PDF, which would tell me before I know whether the weather is good or bad, how long, what the probability that is that I have to wait a certain amount of time. Okay. All right, so that works the same. Let's just sort of go through and find the unconditional probability here. And once again, the big picture is exactly what we're used to. The little picture gets a little bit complicated with these step functions that are implied by the uniform random variables. Okay, so again, the thing that's tricky is going to be kind of like a side point, really, and I'll try to highlight, I'll try to cordon that off from the main process and highlight the big picture here. Okay, so because the component PDFs, the two conditional PDFs, are their step functions, yes, 1/10 for this case, 0 for the other, 1/20th, etc. We're going to expect our unconditional probability to also have cases like that. Okay, so let's just think here. Let's first think about what the easiest case would be. So for X less than 0 or X greater than 20, f of X should be 0. Why should it be 0? Because in this range, when X is less than 0 or greater than 20, this is 0 and that is 0, okay? Both of the conditional probabilities are 0, so taking the weighted average of 0 and 0, we're going to get 0. Fine. What's another case? Okay, we could be in the case of X between 0 and 10, and this is also relatively straightforward. We're just going to plug numbers in to the law of total probability formula here. And so let's do that. F of X is going to be F of X, the PDF for good weather, that's 1/10, times the probability that we have good weather, that's 3/4, Okay, so I'm taking this 1/10 because I'm in that range, and this 3/4 because I'm thinking about the good weather case here. And then we've got the PDF for bad weather here, which X between 0 and 10 is part of the 0 to 20 interval here. So I've got 120 there times the probability that the weather was not good. Okay, so this came from the PDF for not good weather, and I'm putting it here because if X is between 0 and 10, then X is absolutely between 0 and 20, so I have that 1/20th there. And my probability of bad weather here is just 1 minus my probability of good weather. So as always has to happen with the law of total probability, these probabilities of the conditioning events have to sum to 1, and they do. Hooray. Okay, so what does that equal? It equals 3/40 plus 1/80. That's 6/80 plus 1/80 is 7/80. Okay, that's a weird number, but fine. We still have one more case, right? We've got the X is 0, X is greater than 20. We've got X between 0 and 10. The final case that we have to think about here is X between 10 and 20. And in this case, again, I'm just going to put in the numbers from the two conditional PDFs. So for X greater than or equal to 10, it's outside of this range. For X greater than or equal to 10, the probability that the PDF for that range when the weather is good is 0. Okay, so that's 0 times 3/4 plus in this range, X between 10 and 20, the PDF for bad weather is still 120 here, at 120 times 1/4, and that equals 1/80. Okay, that's my unconditional PDF. Okay. So writing it the more normal way here, switching colors. So my unconditional PDF that I'm just summarizing what I just did is 7/80 for X between 0 and 10, 1/80 for X between 10 and 20, and 0 otherwise. Okay. Okay, so let's draw that. It's looks a little bit different. Let's draw and let's also check to make sure that it's a valid PDF. Okay, so drawing it here, I've got 10, I've got 20. What are the other numbers that are significant? Got 7/80 and 1/80. This is not to scale, but that's where those, let's just say that that's where those points are. And what this is saying is that when X is between 0 and 10, then the PDF is up here at 7/80. When X is between 10 and 20, the PDF is down here, and everywhere else it's 0. Okay, that's that same unconditional PDF. Okay, this should make sense, right? Before we know whether the weather is good, the probability that I have to wait 10 minutes or less, the probability for any interval there should be higher, because those events in this range can happen in either good or bad weather. The probability that we have events out here is going to be lower because these things only happen in bad weather. All right. Last thing we want to do is check whether this is valid. Okay, so if it's valid, the probability of the sample space should be 1. So what are we talking about here? What's the area? it should be 1 here. It is this area. Okay. And there's kind of 2 rectangles here. So let's label them. This being A1, this being A2. And what I'm saying is that the sum of those 2 areas should be 1. So let's check here. And A1 is a base of 10 times a height of 7/8. Okay, so base times height equals 10 times, sorry, 7/80. Okay, and the area is 7/8. And for A2, again, we have a base of 20 minus 10 is 10, and now a height just of 1/80. Okay, so again, it's base times height. It's 10 times 1/80. That gives me 1/8. Look at that. That sums to 1. And so if we're given information in this conditional form, and we know the probability of the conditioning event, we can use this version of the law of total probability to find the unconditional probability in all 3 of these PDFs, the PDF conditional on good weather, the PDF conditional on bad weather, and the PDF the unconditional PDF, the one that we use if we don't know whether the weather is good or bad, they're all valid PDFs. Okay, they just apply to different states of the world, but they all obey the Kolmogorov axioms. They all integrate to 1, and they all just follow the rules that we're used to looking at. I think you've seen in these 2 examples that in one sense, conditional probability really is the basic logic flows through with continuous random variables. Things can get a little bit trickier, other situations arise. These are the only 2 examples that we're going to go through in class for 200A. In Brutsakis and Tsitsiklis, they have a few more extensions of, okay, so how does conditional probability work in yet other scenarios? And you guys are well equipped to work through those on your own at the point when it seems appropriate to you.